Hello, I'm Dr. Christy Lukes. In this lesson, we're going to be looking at the Gibbs phase rule. This is not going to be a complete development of the phase rule, that we're just really going to be talking about applications. The first thing you need to understand about using the Gibbs phase rule is the difference between extensive and intensive variables. Extensive variables are ones that depend on size. If you look at the word extensive, you can see that it is the same root as the word extent, right? The extent of something is how large it is, how much it spans. And so an extensive variable is going to depend on size. So things that are extensive variables that you're familiar with are mass and volume, the number of moles we have in a system. These also can be flow rates, whether it's a mass flow rate, a volume flow rate, or a molar flow rate. We're going to find that there are many other extensive variables, but if they depend on size, they all fall into this category of extensive. Now, the opposite of extensive is intensive variables. Intensive variables are independent of size. Temperature is the same whether I've got something teeny or large. That doesn't change how much temperature something has, right? Or the pressure. It's per unit area, so it's already taken into account the size. So no matter what the force per unit area is, it could be applied over a small surface or a large surface. So temperature and pressure are independent of size. Density is another one that you're very familiar with, that's independent of size, because it tells you the ratio between the mass and volume. And then you would multiply that by, say, the volume of your total sample to get the mass. So this is independent of size, density, or its reciprocal, specific volume. Mole fraction is another one that's independent of size. It's just simply a ratio of two quantities, whether it's a mass fraction or a mole fraction. So those are things that will all be intensive variables, meaning independent of size. Okay, they do not depend on size. Well, let's talk about what the Gibbs phase rule is then, and what that has to do with these intensive and extensive variables. Gibbs phase rule will be derived for you more properly in a thermodynamics course. At this stage, I'm just going to tell you this is true and ask you to just be convinced. Okay, we use a scripty letter F, okay, to be degrees of freedom. So F for freedom, that makes sense. It's a little hard to read, that little scripty F. But the degrees of freedom is how many intensive variables may be independently specified for a particular state. So if I am looking at a box of chemicals, okay, I've got a closed system of chemicals there, and they are all sitting there at equilibrium. How many variables do I need to specify to really understand what's happening inside that box? Okay. Now, inside that box, I can have a certain number of chemical species. The number of chemical species we usually designate with a C. We also can have a number of phases. The number of phases in a system at equilibrium we represent with pi for phases. Okay, it's just a common thing to do. And then we may have some reactions that are happening in there that might go to equilibrium. And if so, then I would have R would be the number of independent reactions. Now, I do need to know whether or not my reactions are independent. And if you read in the book, they will tell you a lot more about this. I'm going to come back to this at the end of the course when we actually start needing some of that information when we do energy balances with reactions. For the meantime, read what's in the book. Start trying to develop your understanding of what it means to be independent reactions. Now, number of chemical species is usually pretty easy for people to quantify. Okay, I have a mixture of ethane and methane. Then I have two chemicals. That's not a hard problem. If you have water and ice, those are both water, so that's one chemical. So number of chemical species usually doesn't confuse too many people. Just we have to be careful that water sometimes is described as steam or ice or water. Okay, and all of those really are just the same chemical H2O. The number of phases in a system at equilibrium is sometimes confusing to people. You can only have one gas phase. Gases will mix, okay? If they're at equilibrium, they will mix. Liquids mostly mix, but sometimes you can get a layering of liquids, and so you can have one or two liquid phases. Now, okay, most of the time when you mix things up, they all, stir together nicely. If you put soap in water and stir it, you end up with just one liquid phase, right? You have some bubbles that might have formed, but that's a gas phase. So you have just one liquid phase. But if you were to add some oil to your water, then you would have those two, no matter how much you stirred, they really are not going to stir together. So in that case, you would have two separate liquid phases. So liquids, you can have one or you might have two. Solids, you can have many, many solid phases. Okay? Solids tend to form their own unique crystals. So therefore, if you had a mixture of salt and pepper, okay, you would have both salt and pepper both as the solid phase, so you'd have two separate solid phases. You also can have things like maybe you have a diamond in some carbon dust, okay? Both of those are carbon. It's only one chemical, but it's two separate solid phases. So solids are going to be a little trickier because you can have as many of those as you have chemicals and even more if they form different crystalline structures. So it's pretty much unlimited on the number of solids that you might end up with in your system, but there's always one gas phase, if there's a gas at all. If there's a gas, there will be one gas phase that won't split into multiple phases. Liquids will either be one or two liquid phases. Solids is the one that can go to larger numbers. So we're going to look at three quick little examples. We'll look at the triple point of a pure substance, vapor pressure of a pure substance, and a vapor-liquid mixture of a mixture with two chemicals. Now again, in the textbook, they also do a lot with reactions. We're not going to be doing reactions for a while, so I'm going to come back to this later in the course, but I would like you to independently read this and try and make sense of this now before we get to the material in the future. I am going to emphasize the types of problems that we'll be looking at in the very near future. So first, the triple point of a pure substance. Okay, if it's a pure substance, there's one component. So C is 1. At the triple point, I have the three phases coexisting. That's why it's called triple point. So P or pi is 3. And R, the number of reactions, well, this pure substance isn't reacting all by itself, so therefore I have no reactions. Therefore, the degrees of freedom is 2, it's always 2, plus C is 1, minus 3, minus 0, okay? 3 minus 3 is 0, so I have a unique point. Degrees of freedom is 0. I cannot say anything. If I know that I have a pure substance at its triple point, okay, with all three phases coexisting, nature tells me exactly what is going on in there. Okay, it tells me the temperature and pressure. It will define for me all intensive variables. I would be able to, just based on that knowledge, tell you what the density was of the liquid, the density was, any of the intensive variables for any of those phases. Nature does all the determining for me. Okay, so I don't get to specify anything at the triple point of a pure substance. Nature does it all. Now, I can still talk about size. That is something that comes up later. So, I might say that I have one little solid crystal in a whole bunch of liquid and just 3 or 4 bubbles of gas, right? So I can specify how much of each quantity I have, but those are extensive quantities. Nature gets to determine all of the intensive properties. So let's look at the next one, the vapor pressure of a pure substance. So again, it's a pure substance, C is 1. Vapor pressure is when I have vapor and liquid coexisting. So there are 2 phases present. There are no reactions in this pure substance, so therefore the degrees of freedom is 2 plus 1 component minus 2 phases minus 0 reactions, and so I get 1 degrees of freedom. This means that if I choose the temperature, nature is going to determine the vapor pressure. They are dependent on each other. I can only choose one. I can't choose both the vapor pressure and the temperature. Okay, they are dependent on each other. And similarly, all those other intensive properties, such as the specific volumes and densities, those are all determined by nature. Now, a vapor-liquid mixture of a mixture of 2 chemicals. Well, okay, I have 2 chemicals, so C is 2. It's in vapor-liquid equilibrium, so P is 2. The number of phases is 2. I have no reactions. They didn't mention any, I'll assume that. And so therefore my degrees of freedom is 2. So I can choose 2 variables, and nature will determine the others. Okay? So I can pick temperature and vapor pressure. Nature will fix everything else.